Elizabeth, Londi, Stacy, and myself put together this demonstration of playground physics for you all. You'll see demonstrations of torque on a seesaw, a ramp without friction, free fall motion with a physics book, and a pendulum with a swing. This was done on April 14th in Atlanta, Georgia at the wonderful Piedmont Park. I hope you enjoy.
Here we have Londi and Elizabeth on the seesaw calculating torque.
So what we're trying to find today is how much mass would it take to keep me at equilibrium if I was sitting a certain distance from the pivot point of the seesaw. So first what we're going to do is take some measurements. First, the length of the seesaw. What is that, Londi? 309 centimeters. And now we'll take the radius from this pivot point that is nicely laid out for us on the seesaw. And that happens to be 154.5 centimeters. What now, Londi?
Well, now Elizabeth will be sitting a certain distance away from the pivot point, which happens to be 75 centimeters. Elizabeth?
Now we're going to test our theory so we can calculate the masses.
Whoa!
Not at equilibrium! Alright, we're going to use our handy dandy angle finder and be sure that we are at 0. Looks like we're at 0. So now we're going to do some calculations. That's it. Stay tuned for more calculations and see if we were right. Here we are again at Canlo Park using a swing set to find if the angle of the swing makes a difference in the simple harmonic motion using the pendulum. So first we measured the length from the center, which was 229 centimeters.
Stacy will be getting on the swing, and we will measure from different degrees and determine if the degrees affect the period.
Okay.
This is 20 degrees. Hold on. Okay, we're starting at 10 degrees, and then we'll go from 10, 20, and then 30 degrees and determine how it affects the period.
Okay. So we're going to time her swings using the 5 swings and taking the average due to video constraints. Okay, Londi, got the timer? You have competition at this playground.
All right, ready? On 3, 1, 2, and 3. Two, 3, 5.
Okay.
Okay. 5 oscillations give us
14.6 seconds. All right, now we're going to set up and do the next degrees. 30 degrees.
30 degrees. Yes.
All right, here we go. Stopwatch, please.
On 3, 1, 2, 3.
Woo! Looking good, Stace.
Yay!
Don't let Princess show you up over there.
Stop. Exactly 14.6 seconds.
Wow, so we'll do some calculations, but right off the bat, seems like angle does not affect the time or the period.
Now we're going to find Londi's acceleration on the slide.
So first what we're going to do is use our angle finder to find the angle of the slide. Take it from here. It appears to be 35 degrees. see if our calculations will make sense. Are you scared?
So here we have Elizabeth, and she's on the Princess Tower, and we're going to determine the final velocity of an object in free fall.
Okay. We're going to time it as it falls. Here we go.
1, 2, 3.
There it is. There's our object.
1.2 seconds.
And now we're going to determine the final velocity of that book.
For our first problem, we solved torque on a seesaw. The question we solved for was how much mass would it take to keep Elizabeth at equilibrium if she was sitting 0.75 meters from the pivot point. The equation we used was R1 times W1 minus R2 times W2 equals 0. Our R1 was equal to 0.75 meters. Our R2 was equal to 1.545 meters. Our W1 was equal to 87 kilograms. And our W2 was what we were solving for. After we plugged each number into our equation, our W2 was equal to 42 kilograms. For our second equation we solved for a pendulum. The question was find the period of a pendulum using a swing, and does the period change at different angles? The equation we used was T equals 2 pi square root of L divided by G. Our L was equal to 229 centimeters. When it was converted, it was equal to 2.29 meters. And our G was equal to gravity, which is 9.81 meters per second squared. When we plugged these numbers in, our T was equal to 1.47 seconds. And the different angles do not affect the period because the length of the pendulum did not change. The third equation we used was ramp without friction. Find the acceleration of Londi going down the slide without using friction. The equation we used was A equals G times sine theta. Our angle we found was 35 degrees, and G was equal to 9.81 meters per second squared. When we plugged these two numbers into the equation, our final answer was A equals 5.6 meters per second squared. Our fourth and final problem, we used free fall motion. Find the final velocity of the physics book before it hits the ground. The equation we used was V equals V naught minus G times T. Our V naught was equal to 0 because it started from rest, and T equals 1.2 seconds. And our G was gravity, which is 9.81 meters per second squared. But in this particular problem, G was negative. After we plugged these numbers into the equation, V was equal to 12 meters per second.